The next method is operation action tree. In this method, we have a sequence of activities of a task or a sequence of human error that can trigger a equipment shutdown that's consequence of human error or even accidents. So in this operation action tree, basically we need to apply the probability of each sequence of tasks that can trigger and if one of them we have human error, will have a human error in the activity, or even if there is a human error, you can have an accident. Okay, so this operation action tree here, this example is applied for an accident that we have in aerospace in Brazil. That was a lack of error for the controller and the aircraft pilots. So based on the probabilities that we're defining here, so error 1 to error 6, we multiply the probability, then we have the accidents. Again, the main challenge here is to get this probability. We can use some standards or templates, or you can elicitate based on or specialist opinion. So here we can see, for example, error 1 was a lack of clarity in information accessed by the controller. Syndactor is the controller. And then sequence of failure between the controller and the pilot trigger an accident. The third method is human error assessment reduction technique. This method is more sophisticated because not only enable to predict the human error probability, but also take into account the human performance factor. So the steps of this method is define the activity and this task. Then for each task we need to define corresponding generic task and define nominal human reliability. That's defined in the table. After, you need to define the error producing condition related to each activity. So based on this procedure, it calls error producing condition is the performance factors, and then assess the rate of error producing condition based on this formula here, and then with nominal human reliability we can predict the human error probability. So let's take a look on how to predict this information. So the first one, we have generic tasks. So this table 5.4 here shows, based on this procedure, generic task, and then all what need to do is for each one of the tasks we need to look on which one is similar of is describing here and choose one of this probability. The second step is to look on the error producing condition that we can understand as a human performance factor. So for each one of the tasks, we can have one or more human performance factors or error producing condition. And based on this description here, we look on what is similar with our analysis, and we get these waves here to use in this calculation. So let's give an example. We have the activity to replace valve. To replace valve, we have these 5 tasks. We need to check if operator bypass the line to carry on repair. Check if the lines linked to the valve are failed under pressurized push, isolate valve, and so on. So we have this 5 tasks here, and then we describe this 5 tasks here. So the first one, the first case, we look on which are check and operator bypass valve and repair is similar in this table 5.4. So if you go to table 5.4, we have 0.002. So we consider that respond correct system command event when there is argument to automated supervisor system provide accurate interpretation of system state. So we are considering that this activity here, the general task here, is related with this task in here. So we use this probability. The second step is to define the error producing condition. So our error producing condition are shortage of time available for error detection and correction. So we are using this small time to carry out the task. So we use the wave 11 here. And importance here for this performance factor is 1. That means 100% because we have only 1. So how we are calculating now the human reliability? We have this weight here, so 11 minus 1, we have 10. Then 10 we multiply by 1. We multiply by 1, and then we add we add 1. We add 1 here. In the end, we have 11. So this 11 we multiply for 0.002, and then we've got this value here as human probability error for this task. Okay, let's see this task for replace failed valve with new one. So looking on the nominal human reliability table, we got this value here based on the activity that's more similar with that. So it's this one. So we get this 0.26. So now we have uh, two let's say we have one here, only one in this case, one error producing condition that's operating experience. So we have the wave, that is 3 minus 1. We have 2 multiplied for 0.7. That's a 0.7, that's importance. Plus 0.7, that is 1.4, much plus 1 is 2.4. And then we go again, we look on the second stress factors. 1.3 minus 1 is 0.3 multiplied for 0.3, that's important. It's a 30% of this performance, this error producing condition, and this is 70% of the importance of this one. So 0.3 plus 0.3, 0.9 plus 1, 1.9. And now I multiply this one plus this one plus this one, I got this value. So that's how we predict the human reliability. As I mentioned before, here we have some references that we can apply and use some tables to define probability of error. Another one that is more, I think, is more simple is the standardized plant analysis risk human reliability. So again, this is the evolution, the second generation map that's considered different performance factors to take into account the influence of human reliability. So here we have a table. Here we have only one table. So we have different performance shape factors in here list, and the condition of level of performance shape factors. So for one activity, or we can work on activity level, for example, replace the valve or replace the pump or replace one sensor, we consider the probability factor shape performance factor composite, the PFCFS, as a multiplication of all these factors that are assessed. So for example, in the first case, concerning this replace of this sensor, the available time is equal to time required. So I input in 10 here. The second one is the level of stress, so is extreme stress, so I put a 5 here. And then I assign to assess the performance factors from this specific task and put in the value here. In the end, I got my PSF composition here. That's 187.5. And then I will use this value here and apply in this formula. So what I will see here, that's for this procedure, I have a specific value for nominal human error probability. So the nominal human error probability for commission error is 0.001, and for omission error is 0.01. So in this case, as a commission error, you just put this value here, and then we calculate our probability. So what we can consider in this case is after improvements. So if I consider that now I give more, I will reduce the level of stress from 5 to high, and this experience and training now for 3 to 1. Now I replace the operator, that you change the maintenance technician, that you change the sensor for one experienced one. So that is reduce this value of this factor, and then I can see the impact of my human error probability, that is 1%. So that is the method that enables easier calculation and direct look on some templates. Of course, here this is a procedure. They define the nominal human error probability, but we can again use in another values here based on experience specialist elicitation, or even based on our database. Uh, uh, Another method is success likelihood index methodology. So these methods, again, we need to have a group of experts because it's based on the specialist elicitation about index and importance of each index. We need to define which are the performance factors that influence in this task more, and assign wave factors for each performance factor, and then scoring for each performance shape factors, and then calculate the success likelihood index, and then calculate the success likelihood index, we can calculate the human error probability. So let's consider one activity now, the bearing box primitive maintenance. So I have these 4 tasks in here. For each one of the tasks, I need to first to put some scores for these 2 performance factors I consider is stress and experience. So if I have depends on the level of experience and performance, I put in a scale 1 to 9. So and then if I have a very low experience, I will have 9 as a factor. If I have a very high experience, I put 1, and then this low experience will influence lower in this human error probability for this task. It's similar with the stress. Here I put the stress is high. I just consider the level of stress is high, so it's almost close to 9 here. But you can see that some of tasks are lower than these 2 here. So the second step, since I define the scores for these 2 performance factors, stress and experience, I will put some waves. So the waves is how much percent of one of the performance factors influence in human error. So 90% is stress, and 10% is low experience, and so on. And then based on this value, I can have my success likelihood index value by multiplying and add, multiplying this score plus the waste, and add this one plus this one, and then I will have my score value here. So now I come back to my equation human error probability, and I need to apply log and 2 in the 2 sides here to get this equation here. So now what I'm going to do is I need to define 2 probability values to get the value of A and B in this equation. So if I have the value of A and B, I will be able, based on each success likelihood index, to predict human error in each task here. So that's what I've done. I apply 2 values of the probability error in here, and then I got the values of A and B, and now I can predict the human error probability based on this equation. So I just need to get the slim value and input in this equation here, and then I have human error probability for each one of the tasks, and in the end I will have human error probability for the activity. One qualitative map that is very important is the systematic human error reduction prediction. So this one is a qualitative one. First is constitute the group of experts step. The second step is define the activity and task. Then I will have specific codes, task codes, and then based on these task codes, I direct for the rest of analysis. I give, for example, I will need to, I will be able only to show a group of definition of human error, human performance factors, and of course, I will assess the consequence and recommendation. So based on this procedure here, we have this definition of the human error definition. So those are the codes for actions. I have 5 codes. So action omitted, wrong actions, and so on. For checking, I have other 5 codes, information entry, another codes, and information by itself, other codes. So based on it, I will get, let's say in a railway application, bearing box again, repair. I have 5 tasks. So I define my task in here. Then I define the codes. So base are to make simple, we define all for all tasks a wrong action. So if you look on this table is code A5. Then now if I wrong action, I know there's a commission error. So human error description, I describing here to have a clear understand. So in the first case, they need to open the bearing box, and in the human error case is wrong bearing box opening. So I can put the human performance factor here. It's very important because this human performance factor is the key point to define the recommendation. And to implement the recommendation, the criticality of the recommendation implementation is based on the consequence. So here, for example, if I open wrongly, I will delay in Borenbeck's repair. So what's the recommendation to avoid that? So I start to put the recommendation. Very simple methods, qualitative methods. We're going to see an example based on the FMA application in the end of the presentation.